in the last couple of classes, we have been discussing a lot of things. In the first few classes, we discussed a lot about spin physics, basics of NMR, then internal interaction parameters, especially the chemical shifts, coupling constants, etc. we discussed, varieties multiplicity patterns in coupling pattern, and then we use those knowledge to analyze one dimensional spectra of varieties of nuclei including proton, carbon, tin, etc. We got the idea how to analyze the 1D spectrum. They are all first order spectrum, amenable for first order, very simple spectrum, very easy to analyze. The spectra which we chose was like that. I can see here there is a peak, here there is a peak. These correspond to one functional group like CH3, this for benzene, this is for CH2, like that. That is how we used to interpret, that is how deliberately such type of spectra were chosen which were easy to analyze. And then also after that I wanted to introduce Fourier transformation to see how while getting that such type of spectrum different theorems of Fourier transformations are used. You analyze the spectrum, but you should know how you got it. For that we introduced Fourier transformation and we discussed lot about Fourier theorems and everything. Lot of time we spent on that to understand, and I explained how they are used. All these theorems are useful in NMR spectroscopy when you are recording the spectrum. If you understand these theorems carefully, you will know what are the problems, how you can rectify them while you are doing your experiments. So mathematical tool, especially the Fourier transformation, is very important in NMR. Of course, next thing is I wanted to talk to you about phase and receiver phase and transmitter phase. That is the pulse phase, also called transmitter phase. That is what is important when after I discuss the Fourier transformation about real imaginary part, real part, etc. This would have been apt, but then because of the time shortage, and I will come back to you after this thing, but I wanted to bring that at the time when I am using the phase cycling and product operators. So we will delay that and I will come back to that topic later. It does not matter, it can be discussed at any time. But today I am going to start with quantum mechanical analysis of the coupled spin systems. Remember, in my previous course on basics, I gave a lot of examples about spin system nomenclature, how do you analyze the spin systems, but without getting into quantum mechanical analysis. We analyzed how does I just briefly discussed and showed you a number of examples. How does the AX spectrum comes, how does the AB spectrum comes, what is an AX spectrum, what is an AB spectrum, what happens if there are 3 spins coupled, etc. A lot of things we discussed. Those are all very much useful. That knowledge is essential to understand these things. At least it is needed. So if those of you who miss this, again it is mathematical oriented, this course, this part. If you miss something, please refer to that and you will get the point. Okay. So with this we will start with quantum mechanical analysis of coupled spin systems today. But first of all I want to include what is called a Pople nomenclature. Pople nomenclature means if there are n coupled spin systems. What is a coupled spin system? All the nuclei, if there are then many nuclei, if they are present in the molecule which are NMR active, they may be coupled to one another. Okay, A may be coupled to B, B may be coupled to C, C may be coupled to D something else. Different protons or different nuclei, NMR active nuclei. It could need not be homonuclear, it could be heteronuclear also. Then they all form a coupled group of spin systems. They are called coupled spin systems. If I have spin half coupled nuclei which are coupled spin system, then each nuclei can be spin half nuclei can be represented by a Roman alphabet like this, A, B, C, D up to Z. Okay. But then while referring to that, there is a rule you have to follow. Let us say I take this carbon coupled to proton. I cannot call this as AB. I have to put the nomenclature depending upon how far they are separated in the chemical shifts. For example, in the 500 MHz NMR, proton comes at 500 MHz, carbon comes at 125 MHz. That means they are far away separated, several megahertz away. But what is the coupling between this and this? Carbon proton coupling is of the order of 150 Hz or less than 200 Hz sometimes. Where is megahertz? 500 megahertz, 300 megahertz, and where is 150 Hz? It is very small compared to that chemical shift. That is why such type of system where the chemical shift separation which are much larger than the coupling, they are called weakly coupled spin systems. And such systems we have to define the letters in such a way, if their chemical shift is far away separated, A is here, you have to put X or Y like that. I am sorry. Like see, so you have to put letter which is far away from the Roman alphabet. If on the other hand chemical shift separation is very small, one is here, other is very close to that, and their coupling between them is also comparable. In which case you have to represent by the letters which are closer in the alphabet. That means if you have the two interacting spins represent by two letters which are closer in the alphabet, the strongly coupled spin systems. They will not be, it is not possible for you to analyze such spectra in the first order way. They give us a second order spectra. Whereas the chemical shift separation is far away compared to the coupling constant, some 50 times, 100 times difference. You take the ratio of the scalar coupling over chemical shift difference. The ratio if you take it, this is very large, this value is very small, 0.001 like that. In such type of spin systems are weakly coupled, they give us the first order spectrum which are amenable for easy analysis. Straightforward analysis is possible. That is what we analyzed all the spectra which took as example. So now you know how to put the nomenclature for the coupled spin system. A to X different Roman alphabets, depending upon they are strongly coupled or weakly coupled. You have strongly coupled spin system, letters which are closer in the alphabet, weakly coupled letters which are far away in the alphabets. Okay, this is what it is. So then if they have a second order relationships, in which case strongly coupled can be represented as AB, ABC, ABX, AB2, even A2, A3. They are all highly strongly coupled spin systems. For weakly coupled, we can write as AX, AMX, AA prime, AA2X2 like that. Then what are these prime notations? Why did they write the prime? The prime are the ones such nuclei are chemically equivalent. That is very important. They are chemically equivalent nuclei. Such nuclei we represent by that means AA prime means A and A prime, there are two spins which are chemically equivalent, but there is a coupling between them. Similarly, there are two spins which are chemically equivalent, AA prime and BB prime are chemically equivalent, but between them there is a strong coupling. AA prime is strongly coupled, BB prime is strongly coupled. Between AA prime and BB prime they are strongly coupled. Then we can represent by prime notation like this. Then what is this type of notation? Subscripts. They are magnetically equivalent spin system. For example, there are two, let us say I will take to CH2, CF2, some hypothetical molecule. Fluorine is heteronuclear which is far away separated. Resonating frequency is several megahertz away. Then what happens compared to proton? This, let us say I call this as A2, I call this as X2. They are magnetically equivalent spins, F2 let us say. Proton is equivalent, two protons magnetically equivalent. We call it as A2, this is called X2. We call the spin system as A2, X2. Weakly coupled but far away separated spectrum, that such type of spectra are easily analyzable. So this is how I gave you a brief idea about how to give the nomenclature for the spin system, coupled spin system. More we discuss about the proper nomenclature in the previous class. All of you can see the previous course and you will understand. Simple term, remember, for understanding weak and strongly coupled spin system, you take delta by J or J by delta, does not matter. If a J by delta is very small, very small like this, 0.01001 like that, J, if the J comes in the numerator, chemical shift difference comes in the denominator. If you take this ratio, then if it is very small, 0.0001 like that, they are called weakly coupled. Okay. Also you can take this one, chemical shift separation divided by the coupling, they are very large. If you take the reverse ratio, if it is a very large value, more than 50 times, then they are weakly coupled. So spins can be, if I take this strongly and weakly coupled spin system, they can be weakly coupled or they can be interacting and non-interacting. For example, I have two spins A and X next to each other. Their coupling may be 0 or they may have a coupling. Coupling is non-zero. Both are possible. If their coupling is 0, they are uncoupled spins. Otherwise, they are called coupled spins. Now, if I take consider two uncoupled spins, A and X, there is no coupling at all. They are two independent spins, spin of nuclei. That means they are not equivalent. A and X means they are two different cases. There is no chemical equivalence or no magnetic equivalence as per my Pople nomenclature. That means chemical shift of A is not equal to chemical shift of X. And if the coupling is 0, what is the type of spectrum we expect? Very simple. Let us consider the energy level diagram. When there are two spins which are present, either interacting or non-interacting, does not matter. There are possible orientation of the magnetic energy states if you consider. Both spins can be down like this, beta beta, or one up one down, it is alpha beta, this down this up is beta alpha, both are up, this is called alpha alpha. Now the total magnetic quantum number for each energy state Fz is given by Mi of A plus Mi of X. What is magnetic quantum number of A for alpha and beta? Alpha is equal to plus of, beta is equal to minus of. Now for in this case both are beta, minus of plus minus of is minus 1, whereas this is 0, plus of and minus of. This minus of plus of 0, this plus of is 1. So now the transitions are allowed between these as per the selection rule. I told you between these transitions there are allowed transitions. For example, transition between this to this is allowed. A will alpha of A can go to beta of A. He start from first one. Alpha of A go to beta of A. Here alpha of A is going to beta of A. Allowed transition, plus 1 to 0, 0 to minus 1, both are allowed. Here alpha of X is going to beta of X, that is allowed. Here alpha of X is going to beta of X, that is also allowed. This is X transition. So this is A transition, this is X transition. But what is the frequency separation? Both are same. You see, there is no separation in the energy level between this and this, between this and this. They are all same. So that means both A transitions have identical frequencies, both X transitions will have identical frequencies, and we get two frequencies for A and two peaks for X, but they are overlapped. As a consequence, they give rise to a single peak for X, single peak for A. Which is A, which is X is my nomenclature, depending upon which chemical shift is coming, whether high field or low field. That is only a nomenclature I have given. It is my decision. In this case, I have assumed that delta A is more shielded coming to this one than X, not B, it is X. Than B, I call it as delta X. So now there are two well separated peaks. Actually, there are two peaks overlapped here. So only get two peaks in uncoupled spin system. Now I will consider the example of two weakly coupled spin system, in which case A is coupled to X. Coupling constant is JAX. Since I said AX, chemical shifts are not same. Chemical shift of A is not equal to chemical shift of X, and similarly JAX is also not equal to 0, because as I said this is non-zero, and delta AX is very much larger than JAX because I call it as weakly coupled. I told you strongly coupled and weakly coupled spin system are represented by, weakly coupled means letters which are far away in the alphabet, which I have taken as A and X here. So as a consequence they are weakly coupled. Delta AX is sufficiently larger than JAX. Now when the spins interact with these things, how does the energy level get modified? Accordingly we get the transitions. For example, mz of A and mz of F you take, both are alpha alpha states. What is going to happen? They are unpaired spins. Unpaired spins, they are like spin. What is going to happen in the case of this? Their energy is unstable. They are a bit unstable. They require more energy to get themselves paired up like this. Similarly, if I take alpha beta and beta alpha, they are paired spins. One is plus of, other is minus of. They are paired. Here both are plus of, minus of, minus of. They are not paired. They are unpaired. These have more energy. These have less energy. As a consequence, what happens? Alpha alpha and beta beta states get destabilized and goes up by J by 4. I will show you the diagram now. Whereas alpha beta and beta alpha are stabilized. They are pushed down by the same energy. This will go up, pushed up. This will come down by the same amount of energy. And now if I have the energy level like this without any interaction, without any coupling between two spins A and X, there are 4 spins like this. Now 4 energy states like this. Now alpha alpha if I consider, or beta beta, both of them are destabilized and goes up by J by 4 plus J by 4. Now alpha beta and beta alpha get destabilized by minus J by 4. Now same allowed transitions, minus 1 to 0, plus 1 to 0, this to this and this to this. There are 4 allowed transitions. You can see that all this is allowed A to A, and this is also allowed A to A, this is allowed X to X, this is also allowed transition X to X. Now frequencies are not identical. Earlier case when there is no coupling, there were identical frequencies, they were overlapping, but in one case the energy level separation is larger, in other case energy level separation is smaller. That means the frequencies are not same. As a consequence, what will happen if you calculate the energies of these states? For spin states alpha alpha, we have one energy. For spin state beta alpha beta beta alpha, you can calculate the energies like this. Okay, and without going into the rigorous mathematics I wrote earlier in the previous course, today we will go into the mathematics and try to understand how we got this thing. These are the energy states, we call it as eigenvalues. So 4 in spin states, 4 eigenvalues are there. Using this we can get the frequency of the transitions. You can find out what are the transitions. Even you can assign the peaks for each of the transitions like this. So now if you go to the chemical shift of A, at the site of A, you have one peak towards the right shifted by certain frequency, one peak towards the left shifted by the same frequency, same amount of. So now if this is delta A, this is increased by half of Jx, this is decreased by half of Jx. You understand? So this is what is going to happen, and you get 2 peaks because the energy levels are now frequency of transitions are different, and this separation is called interaction strength, coupling constant, scalar coupling constant JAX, A and X. Identically you see that in the X spin case also. This is A, this is X spin. Same you get 2 lines, separation is JAX. 4 peaks you got, and you got 4 energy levels. This is what, for the beginners who did not come to my last class, I wanted to brief you. Now how did they get this one? I gave only the table, but how did we get this? The rigorous mathematics is there through which we can understand. So today we will try to understand the quantum mechanical treatment of a AX spin system, 2 spins coupled. Okay. For example, if I have to take the quantum mechanical analysis, if I have to do, first step is I have to define the basis set of basis functions to describe the spin system. I have a spin system, I have to decide, set what are the basis functions, set of basis functions I should define. That is the first step. And second step, once I know this basis function, then I have to build the Hamiltonian. Now what are these basis functions for the spin system? And then we start with basis functions. When we start with the analysis in quantum mechanics, to the first approximation these basis functions are the true wave functions. There is not much difference. Basically we start like that. These start initial first approximation what we do for the basis functions, they are nothing but the true wave function, close to true wave functions. And for the nuclear spin system which we are dealing with, nuclear spins, NMR what we are dealing with, the basis functions are to a very good approximation, they are nothing but product functions of the exact wave function of the individual spins. What it means is, I have the wave functions of the individual spins. What are the exact wave functions of the individual spins? If I take one spin, one is alpha, other is beta. There are 2 possibilities. Now the basis function, if I have to take 2 spins coupled, which I showed you in the case of A and X, we have alpha alpha, alpha beta, beta beta and beta alpha and beta beta. What does it mean? Here the combinations, the basis set what I have chosen are nothing but the very good approximation, nothing but the exact wave function of the individual spins. So 2 individual spins, there are 4 possible combinations of these wave functions. They are nothing but the product function, the product of the basis functions which you have to choose. Okay. Once you know what are the product functions, So in the second step, what you have to do is you have to define the Hamiltonian. Of course, Hamiltonian of this nuclear spin interactions, if you want to define, it is different for the solution state and it is different for the solid state. Solid state, there are different type of interactions coming. Since we are not dealing with the solid state right now, we will not worry about it, we will concentrate only on the solution state Hamiltonian. Okay. Now, if I have n nucleus present interacting with each other, several n nuclei are present, each nuclei interacts with the external magnetic field, correct. I have two spins A and X. A can interact with Z1 magnetic field, Z1 interaction can be there. X can also have a Z1 interaction. If there are n number of spins, each of them can individually interact with the magnetic field. Each of them can have a Z1 interaction. Okay. And in addition to that, there is also a scalar interaction between the nuclear spins. Let us take the example of two spins, A and X. A can interact with the magnetic field, there is a Z1 interaction. X can interact with the magnetic field, there is Z1 interaction. Between A and X, there is a scalar coupling mediated through covalent bond. There are three types of interaction if I have two spins. Two chemical shifts, that is the Z1 interaction of the interaction of the magnetic moment of individual spins with the external magnetic field, and other is scalar coupling. Both are present. These two interactions you have to consider and then build the Hamiltonian to carry out the analysis. That is what we have to do. Once you do get the build the set of basis functions, build the Hamiltonian, what is the next step? Third step is determine the energy levels of the spin system and describe true wave functions in terms of the linear combination of the basis functions. Here, that is what I already explained to you. For the nuclear spin, basis functions are for a spin of nuclei alpha and beta. Now, if I have to consider two spins, what is the correct wave function? The correct wave function is the product of the functions of individual spins. That is what I said. If I have two spins, the product functions are alpha alpha, alpha beta, beta alpha and beta beta. So, this is the especially for the nuclear spin basis functions, it is very easy. Basis function alpha and beta you would consider they are nothing but the product function, that is the correct wave function. So, if I have n nuclear spins interacting, I took the example of two spins. Two spins interacting with each other, we have four possible spin states, four possible basis function, wave functions we got alpha alpha, alpha beta, beta alpha, beta beta. Instead of 4, let us say, instead of 2, let us say 3 nuclear spins are interacting. How many you can think of? Each of them will have alpha and beta spin states. So, various permutation combination you can think of. Then it is 2 cube, 8. There are 8 product functions will be there. If you go to 4 spin, 16 will be there. So, the general formula is for n coupled spins, there are 2 to the power of n product functions. You understand? For n the spin of nuclei, if they are coupled among themselves, there will be 2 to the power of n product functions. Now, we will consider a single spin half nucleus, only one nucleus. Let us not bring in J coupling at the moment. If there is one spin, there is no J coupling. The Hamiltonian is given by minus gamma h cross B naught into I. What is this? It is nothing but a Z1 interaction. So, this is already we have been discussing right on the first class. So, this one gets modified because of the chemical shielding of the nuclear spin. I told you the Z1 interaction is there, and then because the internal interaction shielding effect will be there, then this Hamiltonian gets modified now. How it gets modified? It is like this. So, if I consider this one, I consider this as, I write like this, gamma I over 2 pi into B naught into IZI, that we know, we knew the resonating condition. Now, this modification term what we have put is 1 minus sigma I, which is due to chemical shielding, screening constant we discussed. So, now the Hamiltonian without taking into account scalar coupling gets modified because of the chemical shift is like this. So, this is the Hamiltonian only considering interaction of the nuclear spin with the magnetic field, taking into account the chemical shielding. Okay. Now what I will do is, the Planck constant here is dropped. Why did we will drop it in to convert this in terms of hertz? Very easy. So it is, in future when you go ahead, every time to have this gamma and go over 2 pi, getting this 2 pi term is little messy. To avoid that, we remove that gamma over this thing. So Planck constant term, and we write it as gamma I over gamma I over 2 pi into B naught. I is the nuclei of your interest. There could be n number of nuclei. So the Zeeman Hamiltonian can now be written as H of 0. This is I call it as a H0. For scalar coupling, I will put different number. For H0 is only the direct interaction of the nuclear spin with the magnetic field, taking into account the chemical shielding. This is written as I equal to 1 to n nu I I z I. Okay. This is what the Zeeman Hamiltonian we have written. Because I have written nu as equal to gamma b naught over 2 pi, gamma b naught over 2 pi, I remove that and put it as nu, expressed in terms of hertz, frequency units, as Larmor frequency. Then it will become nu I I z I. That is all. Very simple. I have not done anything. If there are n interacting spins, I sum it over n to I, because they are all individually, each of them are interacting. Okay. Now, if there is a scalar coupling, now I bring in another nuclei, and if it is interacting also, in addition to that, what is happening? We will write Zeeman Hamiltonian, plus we also bring in the interaction between nuclear spin I and J. I and J are interacting. Okay. And coupling constant is Jij. This is scalar interaction Hamiltonian. I can depending upon number of spins, I can take 1 to n. This is n plus 1 to other number you can take. If you want n is equal to 1 to I is equal to 1 to n, and the m you can put n minus 1 to j, some number you can write, so that you will get all possible combinations of that. Okay. And of course NMR interaction is mutual. If 1 2 is J12 is there, it is also equal to J21, both are same. So you have to consider only one thing. You do not have to consider, if you consider the J coupling of 1 2, you do not have to consider 2 1. So it does not matter. So this is a simple way you can represent this Hamiltonian. So this is J coupling Hamiltonian, taking into account interaction between the two nuclear spins. Okay. Now this J, I and Ij, we can resolve into 3 components, x, y and z. This is a vector. So I resolve into xi and xj, okay, and then yi, yj, it is a product. Okay. So xi, of course this should have been, y and j should have been subscript, but by mistake I did not put, but don't worry, they are subscript. Like xi, it should be, xj should be subscript, yj, zj, all the 3 should be subscript. It is only the nomenclature, that is all. So now this Hamiltonian expanded into 3 components. J ii dot ij, I wrote in terms of x, y, z components of the vector. Now for example n is equal to 4, there will be 4 H0 terms. I say 4 nuclear spins are interacting. How many H0 terms are there? Each nuclear spin have a separate Zeeman interaction. There are 4 H0 terms, that is why I wrote nu I I z I. So nu 1 I z1, nu 2 I z2, like that there are 4 Hamiltonian terms, therefore H0. But for this one, there are 6, because for 4 nuclei you can consider as 1 2, 1 3, 1 4, 2 3, 2 4, 3 4. There are various combinations you can think of. There are 6 H1 terms here. So it's very simple. Consider 4 interacting spins. The Hamiltonian becomes so complex, there will be 4 H0 terms and 6 H1 terms. Now you may ask me a question. What about radio frequency pulse you are applying? Are you not perturbing the spin system? Is there no interaction with the RF? External interaction is there, like Zeeman interaction we discussed. External interaction, 2 things. One is Zeeman, other is RF. RF also has an interaction, but we will ignore it. Okay, right now external perturbation we do not consider, because we are considering only steady state. We will not bother about it at the moment for calculations. Okay. So basically the total Hamiltonian can be written as H is equal to H of 0 plus H of 1. H of 0 is the Zeeman Hamiltonian, H of 1 is the scalar coupling Hamiltonian. These two can be individually considered. So what you do is you have built the Hamiltonian, you have known the wave function, the energy level of the system you have to compute now. What you will do? In simple basic quantum mechanics you would have studied, you have to solve this time independent Schrodinger equation, that is h psi equal to E psi. We have to solve the time independent Schrodinger equation, then you write this, solve it, and you are going to get eigenvalues and eigenfunctions, everything. That is the basic thing. So, you understood what we have to do for quantum mechanical analysis. You have to build the Hamiltonian first find the wave functions, which are nothing but the product function for the nuclear spin, do the first approximation, but there are also true wave functions. Build the Hamiltonian. One Hamiltonian is the Z1 interaction of each individual nuclear spins, other is coupling among nuclear spins. So, all these things together you have to consider total Hamiltonian and then solve this equation, so time independent Schrodinger equation, and for that you need to solve it in a matrix form. You have to write it in a matrix representation and then solve it. So, for n spins, remember there are 2 to the power of n product functions, and for 2 spins there are only 4 product functions. That is what we discussed. For n spins 2 to the power of n product functions are there. For 3 spins 2 cube, for 4 spins 2 to the power of 4. For 2 spins we are dealing with only 2 spins, because if you want to make the quantum mechanical analysis for 3 spins 4 spin, it will take almost entire course. You will take pages and pages, hundreds and hundreds of pages of book, start working out everything. It will take almost half a year for you to solve all those things, even if you go to 4 or 5 interacting spins. So, right now, but I will tell you the method of solving this by solving the Hamiltonian by taking only 2 spins where there are 4 possible product functions. Okay. So, what we have to do? Construct the matrix, diagonalize the matrix to get the eigenvalues, and eigenfunctions are the linear combination of the basis product function. And basically you have to write a Hamiltonian like this. I am sorry, this is a matrix like this. Hmn minus e to the power delta mn equal to 0. H are the each individual elements of the matrix, and delta mn is the Kronecker delta. For m equal to n equal to, this is 1, otherwise it is 0, and then E is the energy eigenvalues we have to work out. So, Hmn are matrix elements, and for this is equal to 1 for m equal to n and 0 for m equal to 1. So, matrix you have to write in the expanded form like this. For nuclear spin system, for n2 spin I wrote H11 one element, H12 2 3 like this, and then of course the same thing what is shown below. You have to solve this one equation, and then wrote representing the matrix form. This is a 4 by 4 matrix because there are 2 spins, 2 to the power of n product function. So, it is a 4 into 4 6 matrix. There are 16 elements here. If you now nuclear size if n becomes larger and larger, imagine you take 3 spins, there are 8, 2 to the 2 cube 8, 8 into 8, 81 elements of the matrix. That is why I said beyond 2 spin quantum mechanical analysis, if you want to do manually, it is very difficult. Okay. For 4 spin, 2 spin is 4 by 4, for n spin it will become larger. So, now what we will do is we start analyzing the 2 spin case quantum mechanically, considering only 2 examples, 2 cases. The case A and X can be coupled to each other with a coupling constant 0 or with the coupling constant non-zero. We have to consider these two different cases. When J equal to 0, chemical should nu1 is equal to not equal to nu2. We need to consider in this case only H0, because J coupling is 0. H1 you do not have to consider at all. I told you. When J is not equal to 0, nu1 is not equal to nu2, you have to consider both H0 and H1 and then start building the Hamiltonian. Okay. So, now with these are the things, now the time is up. What I am going to do is, in the next class we will take 2 example of 2 coupled spins, work out both the cases where J is equal to 0 and J is equal to non-zero, and get the eigenvalues and find out the transition frequencies and see how the spectrum comes. This is basically what is done for all other coupled spin systems, and we take the example for strongly coupled spin system for AB also and A2 also. For AB we will work out, A2 we do not work out today, it is again a lengthy process will be there. Once we know AX and once we know AB, rest of the things is easy, and for higher spins it is enormous amount of labor work, so we do not do that, and then I will just show you diagrammatically how the energy level works, because some of the stalwarts have already done it and given us the charts. We can utilize that. And beyond 3 or 4 spins, it is humanly impossible. You need to use the computers to simulate and then get diagonalize the matrix and get the eigenvalues and eigenfunctions, etc. So I am going to stop it here today. So we have understood something about today I started introducing about the quantum mechanical analysis of the coupled spin systems. I introduced Pople notation, what is strongly coupled, what is weakly coupled spin system, their notations, and I told you how we have to build the Hamiltonian for the coupled spin system to analyze. And first of all, you have to take H0, H1, etc. H0 is the Zeeman interaction, where the magnetic moment of the nuclear spins are interacting with the external magnetic field. It is a Zeeman Hamiltonian, which is equal to minus nu I Zi. For n spins, you have n number of terms. Then for H1 is the interacting term, which is scalar coupling terms, which among themselves, nuclear spins themselves can interact due to scalar coupling. Then we have to build it as H1, that is Jij I dot Ij, which we remove the x and y component, it will become Iz I Izj. Of course, we can work out and show that later. And then I showed you for 2 spins, we take the example, there are 4 possible product functions, okay, and then we can build the Hamiltonian and start analyzing for both the cases. So we will do that in the next class. Thank you. I am going to stop it here.